All right, welcome back to the Synthesis Workshop podcast. Today, I'm actually joined by Professor Marvin Parasram, who is an assistant professor at NYU. Actually, interestingly enough, I actually worked with a couple months back. We put out an episode. Emma Garganu was kind of the presenter for a Synthesis Workshop, so she had done an episode for the alkene, I guess, oxidation. So with their Nitroarenes, so that was a very fun episode. And now we're putting out a advanced organic course with and she's actually another one of the presenters on halogen atom transfer. And I'm actually the one editing that video, so I've been working with Emma on that. So I guess that's how originally I got interested in your work in particular. But I thought that was interesting. So I'm excited to have you on today. I guess to get started, start with a little bit of your background. I guess what's nice about your group website is you actually put on your hobbies and like ethnicity, which a lot of people don't do. Right. So you grew up in the Bronx, which is really cool. I'm also from the Northeast suburbs of Philadelphia. I've been up to New York a few times. I've never been up to the Bronx though. I assume you're a big New York Giants and Yankees fans. I don't know, but perhaps you could tell us a little bit about growing up in the Bronx a bit. It's quite a unique place to grow up.
Yeah, thanks for noticing that. So the point of putting those things on the website is for people to really get to know us and see us as just regular individuals, right?
Right.
I think most scientists, they display their accomplishments, which is great and important, but they also, I guess a goal of mine was to show that I'm actually just a normal guy, right? Came from sort of a non-conventional background that you would see in most professors out there, right? So growing up in the Bronx is very interesting, right? If you go and ask people about New York, they think New York is just Manhattan, right?
Right.
But New York is basically the 5 boroughs, right? You have Bronx, Queens, Staten Island, Brooklyn, and Manhattan. But even as a Bronxite, we still have Manhattan dreams, right? We at least the rest of the 4 boroughs know that the city is Manhattan, right? It's very interesting. So the Bronx is sort of like a place where you just go for 3 things, right? The Bronx Zoo, the Botanical Garden, and a Yankees game, right? And you really don't see the rest of it, but you'll find that there's more native New Yorkers in the other boroughs than Manhattan, right? And so it always felt like, this is real New York. The Bronx kind of lives up to the stereotype. It is kind of a rough neighborhood, right, in certain areas. Now a lot of areas are becoming gentrified, so South Bronx is becoming very gentrified now, but I'm sort of like in the, I guess where I'm from, it's most famous for is Jennifer Lopez. She actually lived 5 minutes away from my childhood home. So when they say, oh, you're from the Bronx, you're like Jenny from the block. And I'm like, yeah, but she literally lived a block away from my house.
That is crazy.
Yeah. And so the schooling there was okay. I went to Lehman High School, a public school that doesn't have the awards as Bronx High School of Science, for instance. What we're very proud of, though, is that Cardi B went there. So when I was a senior, she was a freshman. So it's pretty interesting.
That's crazy. You overlap with Cardi B. That's crazy.
So we have some famous people, I guess, coming from there. But
right. No, that's really cool. I think you're right. You hit it right nail on the head there. I think a lot of especially foreigners, international students, when they think New York. And honestly, I mean, even people in America, honestly, like when they think New York, they think of Manhattan. They think of those buildings right on the peninsula, really, I guess you could say, near that financial district. That's kind of what they think of. At least that's what I think of anyway. Obviously, Central Park too, but hang on, where's NYU? Is that located in?
Yeah, so it's in Lower Manhattan.
Lower Manhattan, okay.
Right by NoHo, Soho, East Village area. Yeah.
Okay, I gotcha. So kind of coming out from the Bronx then. So, do you do you recommend any places people go visit up there in the Bronx then? Or, I mean, obviously catching a Yankee game is pretty cool experience, honestly. That definitely is. But I don't know if there's any other places you'd recommend.
Yeah, if you like, So there's Riverdale area, which is very nice, and there's Van Cortlandt Park, which is a pretty, would say, underrated like public park in New York. So in the summertime, they have the New York Orchestra. Um, Go to all the parks in the city, so parks in Brooklyn and Queens and the Bronx. And I remember going to that quite often when I was younger and really loving it. And it was sort of like the area of the Bronx that's, we would say, the nicer area of the Bronx, right? And it was a really nice area. I really like that area, and I would go there from time to time. So Van Cortlandt Park, pretty good area. And then we actually have a beach called Orchard Beach, which is you go through the Bronx and you go to this place called City Island. And it's an island, and they have a lot of nice restaurants, and the beach
Yep.
is right there. And they sort of renovated that area too. So when I was younger, it wasn't so great, but now it's beautiful. So
Yeah.
those are some areas I would recommend visiting.
Yeah, I'm like looking at a map now. I'm trying to orient myself. Yeah, that area on the northeast side.
Yeah.
looks really cool. I also didn't know the Ferry Point was also down, and I didn't know it was
Yeah.
also part of the Bronx as well.
Yeah.
But anyway, respect to the Bronx. If you're ever in New York City, just know go to the visit.
Yeah.
Now, coming up through a younger age, was what were some of your kind of hobbies and interests?
Yeah.
Particularly anything in STEM, or just kind of, I don't know, anything you kind of like doing, through middle school, high school, anything like that.
Yeah, so to be honest with you, the for me when I was younger, hobbies were just playing video games. So I was sort of at the
Respect.
age where where we were just getting into online gaming. So I had this we had a PS2 at the time, and we had to get the network adapter just to connect to the internet. And we used to play this game called SOCOM, Navy SEALs, right, which is sort of like predates Call of Duty and stuff like that. And we had a team, and we would play like clan matches, and we would face people around the world, and we were ranked like 50 out of like 200, and that was like a really cool thing because I felt like I was part of a team.
That's crazy.
I wasn't really into sports, mainly because I wasn't very good at it, but I did enjoy watching the Yankees in the 90s, and of course like the Giants, and I'm still a huge Giants fan. I don't know if we can be friends because you're from Philly. Eagles Giants rivalry is a pretty fierce one.
Right. I honest to God, like, I am from Philly, and I love when the Phillies teams do good, but I'm not gonna sit here and tell you I've haven't even watched an Eagles game this year. I'm a huge like European football guy, so that's kind of where I spend a lot of my time. Look, it's a great day when the Eagles win and the Cowboys lose, but like I'm not gonna be like, I literally haven't watched a game this year though. It's kind of you guys. To be fair, you guys do have 2 Super Bowls. Those 2 Super Bowl games are beyond me. How you guys went on those runs to beat both times the Patriots. Yeah. It's actually remarkable now that I think about it, winning those 2. But quite a downer right now, being a Giants fan. I don't really know, signing Daniel Jones on a long-term contract. I don't know what that was about. I don't really think that was in the best interest, but
yeah, I mean, we were all excited based on the year he had before. He went to Minnesota and beat them in the playoff game, and it was really nice. And we were like, oh, next year is going to be great, which would be this past season. And then this past season was just injury-plagued season, not so great. It was kind of a disaster. But, being a loyal Giants fan is something I'm really proud of. I do like, every time I'm down, I'm having a frustrating time at work, or when I was a grad student, I always look at those Eli Manning playoff games, and it will just motivate me. Okay, even though you're down, you can still overcome.
Yeah.
So
he was the guy who caught it on his helmet, man. Like, I always remember that play, like, just crazy.
Yeah. David Tyree.
Yeah. Like insane. I don't know what's up. Did you guys end up signing Saquon Barkley too? I don't even know. Is he signed to a long-term contract?
So they're thinking about franchising, but I don't know where that's going. He hasn't been signed to a long-term contract right now, so we'll see. I'm hopeful. I really like Saquon. I think he's great. He's also from the Bronx, actually. So that's
okay.
Good.
Yeah, hometown kid then.
Yeah.
At least you're not a Jets fan. My uncle and my cousin are Jets fans, and it's just miserable. Yeah. So
yeah, their season Jets are actually worse than ours.
Their season died. Their season died in literally a quarter, not even like one play. It's really unfortunate, but. No, but I appreciate you sharing that you're kind of into video games. I feel like I grew up playing PS2. I was a bit too young to kind of understand the online multiplayer when the PS2 era, but I definitely played a lot of single player games from the PS2, and obviously now, like, I mean, I played like Black Ops 1, Call of Duty, Black Ops 2, a lot. I don't really play the newer CODs anymore. And I'm not really into the battle royale type games either, but they're still obviously really prevalent today. But yeah, I appreciate you sharing that. I feel like a lot of people actually don't admit that. They play, I don't know.
So I thought I was gonna play video games forever, and then of course, like, I went to college and grew up a little bit, and I was still playing Madden a lot, and then now I'm like, oh yeah, I don't even have time for video games. But something that I remember fondly when I was younger. This is something I would love to do. Getting into STEM was not a clear path for me. So
sure.
I did take AP chemistry, and that's when I sort of started to fall in love with it. But I still didn't commit to chemistry. I wanted to be a pharmacologist, actually. I wanted to do more like how drugs interact in the body, and then I realized it was more biology, and I was like, okay, maybe I took biology in college, so I went to Stony Brook, and I hated it. I just couldn't, like, at least for organic chemistry, you can see how bonds are moving, how things are combining, or you understand these fundamentals, and it makes sense. At least to me, it did. And I remember sitting in that organic chemistry class, and I had these two professors. They're now retired, and unfortunately, one passed away. But they were excellent. This was back in 2005, 2006, and they're teaching organic chemistry, and they had PowerPoints, writing pad. They would record lectures, things that are very common today. They were doing back in 2005, which was not very common, and it was great. I thought they were great educators, and they really made me fall in love with organic chemistry. So then I remember, at the end of my sophomore year, I said I want to be a chemist. I want to do organic chemistry. And then, like most people, they join a laboratory. I did undergrad research with Nancy Goroff. She's now retired and going into sort of the brave section, which is the politics section of her life, which she's running for Congress in Long Island, which is, I think, very interesting. And
that'll take years off your life. Jeez.
Yeah.
But very admirable. She's very obviously, if you're passionate, I get it, but man.
Anyway. I just don't know how she does it, but I respect her so much for doing this, and she's trying to make change, which, you do as an organic chemist, right? You're trying to discover something that will impact the field, and I think she's trying to take it to the next level, and that's great. So I remember working in her lab the first day. I'm doing an N-butyl lithium reaction, and this
first day,
and I'm learning how to do it. And then, of course, like, I'm not following appropriate protocol. Normally you would, have a purge line in, and then you take out with a metal needle that's already hot. There's no water in there. You put it in there, and then you extract the liquid. And then the mistake I made was I pulled out the needle instead of pulling out some inert gas to have that sort of protective layer in the syringe. So when I pulled it out, of course, with force it shot out, and then my whole needle caught fire. And like I luckily had sand nearby, I just doused it in sand, so I did pay attention during the safety thing. But I was so terrified.
That's crazy.
Yeah. And
you didn't have like an older student near you doing this?
Yeah, I did, but before, she was watching me, and then she did help me. She did, like, when I got nervous, and when I saw the flame, she said, "Get the sand," and then I did all that, and it was fine.
Yeah.
And thank God she was there. But I remember thinking, wow, I can't do this for a career. This is like, I already messed up the first go I did. But it was good because I realized that the mistakes you make, you actually learn from them the most. So now I will always know not to do that. And when I teach my students, when they first come here, I teach them the first reaction they do is also an N-butyl lithium reaction. And I show them how to do it first. And because you're going to do N-butyl lithium, organolithium reactions, if you're a synthetic chemist, you do this all the time, right? So I felt like it was an important place to start. And now my students are doing that, and they're comfortable with it. And we haven't had any fires, so that's good.
Thank God.
Yeah. So that was the start. Yeah.
Because N-butyl lithium typically is not as well. It's not as bad, but
it's not as bad. Yeah.
When you get to like tert-butyl lithium, though, then you really starting to push it. Like tritibutyrophosphine. Got to be careful with those. But no, I mean, that's, as you mentioned, that's a great learning lesson. A little story I have is last fall I had a freeze pumped all bomb blow up in my face. Basically, I was doing basically what happened was well. I was doing it on an argon Schlenk line, which I shouldn't have been doing it, but I don't think that was the problem because I was pulling vacuum so I don't think argon condensed in liquid nitrogen. I don't think that happened. Because like I said, the vacuum was on and I was pulling, it was under vacuum. So I don't think there was any condensed argon, but I was doing, I was doing a freeze pump on deuterated chloroform. And basically after the freeze, I took it out of the doer and I started heating it with a heat gun like an idiot. That's okay. I didn't know. Well, to be fair, we got new heat guns, which were extremely hot, and I didn't really know this. Like, I didn't really know this. So in any case, for anyone out there doing a freeze pump thaw, don't apply external heat. Just let it thaw. It'll take some solvents will take a long time, but trust me, just let it thaw normally. Do not apply external heat, and you won't have a bomb blow up in your face. I'm okay now. I only got 4 stitches, so we're okay. And thank God I was wearing goggles. I was wearing a lab coat. Good. So yeah, let that be a learning lesson to someone else now.
Yeah, at least you got a battle scar. That's pretty good.
I don't know if you can kind of see it, but I do have a battle scar, and I can say a bomb blew up in my face. And I survived it, right? So, I know I laugh about it now, but it's a good learning lesson for everyone else. So I think, thank God it could have turned out differently. Like yourself, it could have turned out differently, but it didn't. So now we're gonna learn. I learned from it and take it on to the future. But that is interesting that you had a scary moment, but you stuck with it though. So it didn't really did it deteriorate at all, or you kind of had second thoughts, or you wanted to stick with it, right?
Yeah, I wanted to stick with it. I think I didn't know this back then, but I would always think, I came from the Bronx and I had this tough mentality mindset where I wanted to be mentally tough, right? And I would always keep trying until I feel like I can't do it anymore. So I said, okay, I have to give it another shot. I just never quit at the first sign of failure. At least that's what I learned. That's what I needed to learn to get out of the Bronx. And that's what I have today. I feel like if you get deterred on the first sign of failure, you're not really learning anything valuable, right? And you can miss out on a lot of things. So that was the mindset I had. And I said to myself, you know what, you messed up, you learned from it, let's try again. And then you try again, and then the more you try, the more successful you'll become, right? That's what Thomas Jefferson kind of said when he said, the harder I work, the luckier I become. And I remember that quote sticking with me, and I said to myself, let's just keep going and let's see what happens. And it turned out to be probably the best decision I ever made, because if I didn't continue, I probably wouldn't be here today, right? So looking back, it did work out.
Now, how did you get the opportunity to do undergraduate research? So you were taking the class, and then, what was her name again? I'm sorry, what was your advisor's name again?
Nancy Goroff.
Nancy Goroff. Okay, so was Nancy looking for students, or did you kind of go up to her and say, hey, I'm interested in undergraduate? How did that kind of opportunity arise?
Yeah, so I didn't know I wanted to do a PhD program, but I just knew that I wanted to do more advanced organic chemistry, right? So I remember looking at the website, trying to figure out which research I would be interested in. Of course, like most undergrads, you don't really know advanced chemistry too well, so you look at these websites and you're kind of overwhelmed. I know my students here at NYU, do the same for my website and your PI's website. They'll probably say the same thing. But you kind of look at what interests you. So I know she was doing some polyaromatic hydrocarbons, and it looked like they were doing a lot of synthesis. So I emailed and I said, can we meet? I'm interested in doing undergraduate research. We met, and she asked me about my goals, what I want to do. I was honest with her. I said, I'm not sure, but I really want to do more organic chemistry. And then she let me in her lab, trained me up, and I worked with a grad student. That's how it kind of went on from there. So it was just curiosity. But then after doing that, I realized that, I want to do this for a couple more years after I graduate. So I considered doing a PhD program. And that's how I got into grad school. And then, went to UIC, University of Illinois at Chicago. And that's where I worked for Vladimir Gevorgyan. So that's the next part of the story.
Yeah, I was gonna say, taking that initiative as kind of a sophomore to go do undergraduate is pretty. I would say, I want to say hard to come by nowadays, but I feel like I haven't really seen it as much. I guess one thing I will say is, like, if you are an undergraduate student who's interested in research, just email. Honestly, like, just reach out. Honest to God, like, I more often than not, professors are a lot more receptive, and they'll tell you straight up if they have spots in their labs or not. But I think if anything else, like, it's just a great opportunity to, I mean, just enhance your skills. Like, you don't have to do what we did and go to graduate school, but like, just the people that you'll meet, the skills that you'll pick up, will transcend, I think, your experience in college. And there'll be a lot of transferable skills. So just give it a shot. You might like it.
Yeah, I agree.
So after you graduated from Stony Brook, like you said, you moved on to graduate school in Gevorgyan's.
Gevorgyan.
Gevorgyan.
Yeah.
All right, Gevorgyan. But University of Illinois at Chicago, so another big city. I guess so how did you know that graduate school was kind of the right fit for you? I mean, was it kind of at the end of undergraduate, weren't really looking for a full-time job yet, or like kind of how did you come to that decision to pursue grad school in general?
Yeah, so around this time, 2008, 2009, this is where sort of the market was not so great for getting jobs after college, right? Before that,
the
in
housing
the 90s, yeah, right, the house, yes, exactly. So it was just a tough time, right, financially, and it was, so I said to myself, I know I wanted to get a master's degree actually at first. I said to myself, I should probably join the master's program, where just a year after your bachelor's, you take a couple more classes, do research, and you get a master's. But I felt like it was just a temporary solution, right? I knew I'd probably have to do more training, get more experience to get a good job. So I looked to my mentors at the time in the Goroff lab, and they were also PhD students, and they had a lot of positive things to say about the PhD program. And one that I think that a lot of people don't know about is that the PhD program is actually free, right? You don't really have to pay tuition and things like that. I remember at the time I didn't know that either, and I was thinking, wow, that sounds like a really good deal. You get an advanced degree without paying for it, right? And I get to continue to do organic chemistry. So it felt like a win-win, right? It's like, this is like something that's very attractive. You get a good degree and you get to continue research, work in academia, do advanced science, and you get to teach, right? By being a TA at most places. And I thought it was a really good gig and good thing to do. And of course, I didn't know I wanted to be R1 professor at the time either. So I said, I'm just going to go get a PhD and perhaps go to industry, or maybe teach at a community college, or teach part-time. Because I really did like being a TA. I was an undergrad TA for organic chemistry too, and I loved it. So I said, okay, maybe I should apply to PhD programs. And I have to be honest with you, my stats weren't very good, right? For instance, I got like a B+ in organic chemistry, right? So I wasn't an A student.
That's the sin. That's like that's the sin.
So I knew that maybe getting to PhD programs would probably be a little challenging, and it was. And I got a few offers, and of course you get to visit them and you get to see how it is to work there and meet with the professors. And I remember going to Chicago, and I was like, okay, this is a pretty small city, right? Because everything compared to New York is small, right? And but I'm like, okay, but it's pretty cool. It's like a nice city, and it has a nice river going through it, which I thought was very unique. And I like the department. I like that it was a pretty good department for organic chemistry. And Gevorgyan was very, very good. He was publishing quite a bit, and his research lab seemed very active. So I thought it would be good for me if I go there. And that's what I ended up doing. It was really tough because you're leaving home for the first time, right? Because I've been in New York my whole life, and now I'm going to another city. And in college, I have a twin brother. His name is Melvin, and we were both at Stony Brook together. But now it's my moment where I'm actually leaving him as well as my family and going to a new place alone. And I thought that was pretty overwhelming at first. I remember when I got there by myself, I'm like, wow, what do I do? Right? This is a new place, no friends, nothing. Have to start over.
Yep. Completely get the feeling. When I went to undergraduate, not too far from like South Philadelphia, so not too far from my hometown, and then moving to Houston to graduate school. Very very sad when I had to leave my parents and my brother when they had to get back on the plane to go back. So I understand the feeling. Shit, it sucks, honestly.
Yeah, it was scary. It was like, wow,
Yeah, this is like really it, and now I really got to do it now. But it worked out for the best. I'm really enjoying it now. So but yeah, so you're in Chicago. I mean, great city. Winters are brutal there, but super windy. What drew you towards his lab though? Like what about it kind of wanted you to do research in that lab in particular?
Yeah. So what I'm about to say might sound a little like controversial, but or may not. But the truth is, if you want to be successful, right, you have to get publications, right, and that's how. It's not fair, but that's the way the field views you, right, based on output. And I knew that if I joined his lab, I would most likely achieve that because his vision was you have to get at least 5 papers to get a PhD. And that sounds really harsh, but that's what he wanted. And he felt that if you get those, you'll be competitive to any market you apply to, whether it's postdoc, whether it's industry, wherever. And I remember him saying that in our one-on-one meeting, and I thought it was like, yeah, I also believe that. I also agree with that. And, when you're picking an advisor, you have to believe in their vision, right? Because that's their lab, their philosophy. And if you don't agree with it, it becomes a little problematic later down the road. But I remember sitting there thinking that, yes, I think if I can get 5 papers, I would look really good. It will make me look productive, and I would be competitive, right?
Right.
And, you're not just competing against people at your university, you're competing against people all over the world, right? And how do you stand out? And I felt I could probably stand out if I have good papers. And and I really believed that. And I said, yeah, I want to join this lab. I think if you help me get where you want me to go, which is those 5 papers, and I get those, I think that will set me up for the rest of my life. And of course, your advisor, they're great and they have a lot of wisdom. But I remember thinking that, okay, this is going to be easy, right? A paper a year, right? At least you're naive and think that. But then you realize it's not that easy. It's not that easy getting 1 paper. So, of course, it sounded really good when you're thinking about, okay, average a paper a year. Okay, 5 years PhD program. This makes sense. But I got my first paper in the 4th year. So, it wasn't like a walk in the park as I thought it might be. And but I think the key point is that you have to believe in their vision if you want your interests have to align, right? And I think you'll have people that join labs for all sorts of reasons, but if they don't disagree with your fundamental philosophy, it causes problems down the road. And I remember thinking that I believe in this, I'm going to join this lab, and I'm going to stick with it. Yeah. So that's why I joined his lab, because I really believed in his vision.
Yeah, that's thank you for bringing that up. It's a good point, because I think lab philosophy is something it's obviously it's suited for each PI. And as long as at the beginning people are upfront and honest, I think that's kind of how you cultivate successful atmospheres, I think. So
yeah.
And I think you're right. I think people don't really want to talk about it. Well, people I think a little bit too casual about it when they say like, oh, don't worry about the publications or whatever. But it really is true, honestly. I mean, at the end of the day, you are competing with other grad students who are from, the Princetons, the Caltechs, the Berkeleys, the Chicago, Urbana-Champagnes, like those, like, I mean, those are really competitive schools. And who are also have advisors who are extremely well known. So the only really way for a grad student to get a name is having those names on those publications. That's really that's the truth of it.
Yeah.
So I hear that. Now, chemistry wise, what were you working on as a grad student? Like, what was kind of your contribution?
Yeah, so I also joining his lab, I was really attracted to his research, and I said to myself, I'm gonna stay in a lab for 5 years or more. I want to learn something new. And at the time, going from Nancy's lab to Vlad's lab, like she was doing just polyaromatic hydrocarbon synthesis, so we're using organolithium reactions, some coupling, but nothing really transition metal mediated, right? And Gevorgyan was doing a lot of CH activation. And around 2010, this is when I was in grad school, that was sort of a hot field, right? CH activation was everywhere, right?
Yeah.
And people were activating CH bonds, sp2 CH bonds, and there was a lot of work from the fundamental work from the late Keith Fagnew that was doing CMD reactions, and Jin Kuan Yu was publishing a lot of papers, and it was just an exciting time for CH activation. And that's where he was working. And I remember thinking, oh, this is a field that seems like it's going to be emerging and probably stay here for a long time. And I wanted to learn more about palladium catalysis. And so that's why I joined his lab. He was doing, at the time, he was creating removable directing groups for CH activation. So when CH activation really started, they had these pyridine directing groups that just was left on your molecule, right? You would do a functionalized CH bond, which was incredibly difficult, right? Strong BDE, and you had no control, but the pyridine would control to the ortho position of a aromatic ring, and you would functionalize it, and that was great. But the problem was that the pyridine will still be there, and or the directing group will still be there. So Gevorgyan thought of using a silicon tethered directing group. He would install the silane, have the pyridine attached to it, do CH activation, and then remove the silane or functionalize that site. And that's what he was doing at that time. And I thought that was really, really interesting. So I joined the lab, and so of course, when you join a lab that has a direction, right, and that's established, you're not going to, sometimes you get lucky. It's all about timing, right? If you join at a time where they're starting this project and there's a senior student that has legs, it's great, and you probably get a paper. Or you might start a new project when you join and it has no legs, and you have to work really hard to get something. So I was like the latter. I joined a project that really had no legs, and I was trying to really get something going. And I remember thinking, okay, I got this CH activation to work, but it wasn't, I think Gevorgyan realized at the time it wasn't so great. So he kind of pushed me to think of something else. So I developed this, I had this silicon methyl iodide, right? And I was inserting palladium in between, at least I thought I was doing oxidative addition between that carbon sp3 iodine bond. And the idea here is that the beta position is blocked by the silicon atom, so you won't have issues with the beta hydride elimination. And at the time, alkyl Heck reactions weren't so well established because you would get beta hydride elimination. So we thought we had this really nice strategy where we can just sort of have this blocking group and then remove it later, right? So we were doing this intramolecular Heck reaction with this halomethylsilane, and we can easily attach the silane to like an alcohol. So we had a homoallylic alcohol, we tethered it to the silane, then we do an intramolecular Heck reaction. So at the time, it was really, okay, we were like, okay, this is interesting, but it turned out to be something much better than a conventional Heck reaction. And we found that intramolecular Heck reactions tend to go exocyclization to generate a more favorable ring. So prefer 5-exo over 6-endo, 6-exo over 7-endo, and so on, right? But we found that for our silane, we were getting the endo selectivity, which is the total opposite of like conventional Heck reactions. So then we were like, this is weird, right? It has to do with the influence of the silane, and we couldn't really understand what was going on. And then Alexanian, around the same time, came out with his paper on the alkyl Heck reaction with alkyl iodides. And he proposed a hybrid palladium radical intermediate. And we were very interested in this because we were thinking, how are we getting this selectivity? Maybe it's forming an alkyl radical. We have the silyl-methyl radical. And then maybe that, because of the long silicon carbon bonds, maybe it's going to do endo because it has a geometry to do that, right? It's now a longer bond. It could adopt that conformation to do endo cyclization. So I remember reading Alexanian's paper, really inspired by it, and I started to do mechanistic studies to figure out, are we going through this alkyl radical? And it turned out we were. So we were going through this alkyl radical, and that alkyl radical was next to the silane, and because of that long silicon carbon bond, it was doing this endo cyclization. It turned out to be a really big paper, and it was something that we had some hypothesis, but we didn't expect this outcome, and sometimes that's how great things happen. So I remember thinking, this can't be right. I looked at the crude NMR, I was like, this can't be right, can't be endo. I told my advisor, he also didn't believe me, and he said, okay, get an isolated yield, let's do 2D NMR, let's make sure this is it. So I did all these studies to prove that it was. It turned out to be endo cyclization, and it ended up being a big paper. It was my first JAX paper, and wow. I was very happy about it, and it was good.
It's really cool story. I think see the kind of come full circle then. I mean, coming in full project, and then by the end you're doing mechanistic studies, get that paper. That's really cool.
Yeah.
And it speaks to sometimes chemists don't really know what's going on. They got to like probe
Mm-hmm.
at it. So I think that's
Mm-hmm.
early testament to that. That's really cool that you're able to get that to work.
Yeah.
Yeah, that's really cool. Now, at the end of your time as a PhD student, you decided to go do a postdoc with Abby Doyle.
Mm-hmm.
At what point did you were you kind of like really considering? Well, was it this point you really had you become like considering like doing a professorship, or
Mm-hmm.
like how did that decision arrive to go do a postdoc?
Yeah. So in my, I want to say like my last few years with Gevorgyan, we were discovering something new, and he allowed me to help him write a grant. So Gevorgyan will rely on his senior students and postdocs to help come up with an idea for a grant, and he would train us on how to write grants. So I was a senior student at the time, and we didn't get our R1 funding renewed for the past 2 years. So I knew that we had to think of something big, and I was thinking about this fundamental project, the first paper, right? This methyl radical that was being formed. And I remember thinking, what if we can attach this to a molecule? We form this alkyl radical and it will transpose to another remote site, like a 1,6,1,5 HAT, right? At first, we were thinking 1,5 HAT. But the effect of the silicon, right, having these longer carbon bonds could go beyond 1,5 HAT. So
Hmm.
we found that it could go 1,6,1,7 HAT, which is a bit unconventional for carbon-based radicals, right? And we were able to do that, transpose palladium to another site, and then it would do palladium chemistry at that remote site.
Hmm.
And it was kind of a big find. It was something that we weren't expecting either. And so we would install silane on an alcohol for this aliphatic alcohol, and it would transpose. We formed the alkyl radical at the methyl site, and then we'll do 1,6 HAT. And at that new site, palladium will recombine and do palladium chemistry there. And we didn't need a directing group, nothing. It was just radical character combining with palladium character. And that's the point of Alexanian's term, this hybrid palladium radical. And we were really taking advantage of those two features. And what was even cooler at the time, this was when Photoredox started to emerge, and we were actually taking this palladium and shining blue light on it. And without a photocatalyst, well, conventional one like iridium or ruthenium, we were actually doing palladium photoexcitation, and that was doing SCT. And at the time, that was kind of a new thing. And so Gevorgyan, I remember we were talking in his office, and he was like, "Yeah, this is something that's really great. We should write a grant on this." And we ended up writing a grant together, and we developed a lot of projects. I remember sitting in his office like around 8 p.m. some nights, and we're just talking about ideas. Okay, we know that's going this way. Can we leverage to do another activation event, right? Can we intercept that transpose radical with an alkene and do a remote Heck reaction, for instance? That was one of the ideas. And I remember thinking of, it was fun just thinking about these ideas, and then we would ask the junior students to try them out. And it would work. And some ideas, of course, wouldn't work, but some would. And I remember thinking, wow, this is such a great feeling. This is what professors do all the time,
Hmm.
right? Write grants, come with ideas, and mentor students on how to make these ideas come to life. And I remember at that moment, that's when I knew that I wanted to be a professor. So before that, I was going to industry. I was going to go to industry, no question. I was just like, I'm going to get a PhD, go to industry. But that moment when I was sitting with him thinking about these ideas, that's when I realized that I want to do this for the rest of my life. I want to try to write grants. I want to create ideas, and I want to see these ideas happen. So that was the pivotal moment. So then I knew I had to go do a postdoc.
Yeah, that's really cool. Yeah, I
Yeah,
mean,
yeah,
it's not too often that people get opportunities like that to sit in with your professor and like write grants like that. It's definitely a very unique opportunity.
yeah.
That's really awesome. You were able to do that. Write grants, kind of sit in as a senior member and do that those kind of things. So, yeah. So now you're moving on to a postdoc. I assume is Abby Doyle at Princeton at this time, or is she?
Mm-hmm.
Okay. Um, yeah. So anything why go to Princeton, do a postdoc with Abby Doyle? Like, what was kind of what drew you
Yeah,
there?
yeah. So I'm going to say something else that's a bit controversial too, but if you want to be a faculty member, right, at a R1 institution, unfortunately, you have to, at least from what I've seen, most of them come from top 10 institutions,
Yeah.
right? At least people that are getting interviewed are from top 10 institutions. So I knew that I have to if I want to be a professor, I have to go to a top 10 institution and work for, a lab that's producing papers. And well, of course, the PI doesn't have to be famous, but it has to be productive, right?
Yeah.
But of course, a famous PI will help, of course. So I recognize that immediately, because we would have people come to UIC and get interviewed, and I noticed that all of them were from Caltech, from Princeton, from Harvard, right, from University of Chicago. And I realized that, okay, I have to get in, that if I get into those institutions, they would open these doors that I have to go through. And this is it's a hard pill to swallow, right? Because you have to do this. And I remember thinking, okay, I have good papers, maybe I have a shot to get it, right? And I'm gonna have to be honest with you, it was pretty hard. I applied to many schools, and at this time, unfortunately, timing didn't work out for me again. At this time, this is when NIH set the minimum of postdocs to make 47,500, right? Before, there was no salary set for postdocs. So PIs were paying postdocs less than that, probably 32,000, right? Probably even 23. We don't know.
That's crazy.
But NIH didn't have any guidelines, but that year they set the guideline. And of course, PIs are scrambling to adjust, right? They're used to paying their postdocs less than that, but they have to follow this rule. Some schools are following, some schools aren't. So at that time, it was really hard to get a postdoc job. No school wanted you because no lab wanted you because they didn't know what to do financially. So I remember getting rejected left and right. But I knew I was targeting Princeton mainly because I knew that organic division was very, very productive. It was a top 10 school. The labs there were great. There's students that go through those labs, get jobs. And of course, it was closer to home, right? So going from Midwest, and I kind of wanted to come home. So I remember, asking Abby. I emailed her my application, and my boss sent Vlad at the time. He sent her a recommendation letter. She reached out to me, and we had an interview over Skype. Right, this was before the Zoom era, so we had a Skype interview, and I thought it went pretty well. And then a week later, I reached out to her just following up, and then she said, "Yeah, we'll love to have you join us." And are you interested in writing the NIH F32? And at the time, I was kind of looking for employment, and the deadline was going to be a little past when I wanted to leave the lab. So the upcoming deadline was in August, but I'm leaving the lab in like April, right? So I said, would it be all right to, and the other deadline's April 1st. So I was leaving the lab like April 15th or April 20th or something like that. And I just said it would be too hard because I have to finish my thesis. She said, okay, I can have you join, but you have to write this when you get here. And I said, okay. So then she ended up giving me the offer, which was great, because some labs, they don't do this, right? You have to write first and then get the contract. Right. Some labs just hire you without writing, right? So it really depends. It's PI dependent. But I was thrilled. I was thrilled to be going to Abby's lab. I was thrilled to go to Princeton. And I remember my first day there, I was just like blown away. I've been in state schools my entire life, and then I go to this Ivy League school, and it just looks great, right? The buildings are in pristine conditions. We have a new building, the Frick Chemistry Building, which is built in 2010. Brand new lab space, just beautiful place. And of course, I felt out of place, right? This is a kid from the Bronx that went to state school his whole life, and then this is Ivy League, right, territory. And this is, I was feeling a bit overwhelmed, actually. I was thinking that I don't belong here, right? That's the initial feeling you get. If you're not familiar, right, you're going to feel that way. Yeah. And I remember feeling like this is not for me. But Abby welcomed me. She was very nice, and she was really supportive. And I remember joining the lab, and she would tell me that you're very smart, you're very good. Let's have a good career here with you. And I remember her just her being very supportive, and that helped me feel comfortable. Yeah. So that was very nice. And the team at Princeton, they were just amazing people.
Yeah. It's got to be such a weird feeling, like you said, like going to public schools and then all of a sudden you're at an Ivy League. It's got to be such a weird feeling. Yeah, look, the endowment at Princeton is crazy. Like other Ivy League schools, the endowment is crazy. Yeah. It's some like they could pay every single undergraduate their tuition and it's like 3 times over. And people can go ahead and trace the money. I don't know where these things, they go into their facilities. I don't know where it's going, but it is, if it is a great place to be though if you're a student though. Put it that way, especially faculty, students, postdocs. It's a great place to be.
Yeah, it's great.
And look, the science there is stellar. Like there is some of the best minds there. There's no doubt about that either. Some of the best people are there. But so you're at Princeton now, and what were you working on as a postdoc there?
Yeah, so as a postdoc, I came in and I wanted to learn something new. So at the time, Abby was starting to do like a lot of machine learning stuff, and I remember thinking, I have no idea what this is, and I want to learn. So I joined a project with Ben Shields, and he was this. I thought, wow, this guy. He was a grad student. He was amazing, very smart, and he was trying to push this machine learning project using Bayesian optimization, where the model will learn from itself and do predictions. And, I started and it was good. I really liked it, but I couldn't sit at the desk. I just remember thinking, like, I just want to be at the hood, right? I've been at the hood my entire life, and like, I miss the hood, right?
Yeah.
With the machine learning, of course, you're going to sit at the computer a little bit, and also you need to get some like results for the supervised learning approach. But I just felt like I think this is great, but I really want to do synthetic chemistry.
Yeah.
And at that moment, I didn't. It was hard pill to swallow to let go of this, because I normally just don't give up on things. But this one, I wasn't enjoying it as much as I wish I would enjoy it. And honestly, today I still wish I enjoyed it, because it's kind of like this emerging area that you want to be part of. But I'd rather just be at the hood and like make something, and make some cool like bond forming event that would be a nice reliable method. I just like doing that physically. I just wanted to see that. Of course, you're not seeing these reactions in the flask, but it's there and it's happening. But to me, I was missing that so much. So I remember deviating a little bit and doing some nickel photoredox catalysis, and we were doing cross electrophile coupling. At the time, you needed a nucleophile and arrow halide, and then this was making the carbon sp3 sp2 bond forming event. And the Doyle lab has a lot of interest in cross electrophile coupling, so we were trying to translate this manifold to cross electrophile coupling. So I was coupling epoxides with arrow halides, and we were making sort of beta substituted alcohol, arylated alcohols, and it was all mediated by this process. So that was the first paper, and then I ended up continuing the machine learning stuff. I was doing more of the synthetic work and got a couple papers out that in that area, and then it was time to like go on the market right after that.
Yeah, and now you're at now you moved to NYU. Yeah, definitely. Let's talk about your research now. So you moved back to New York. Great, Lower Manhattan, great place to be. I know you're a Bronx kid, but Manhattan is a cool place to be.
Yeah.
And now you do a lot of aerobic reactions. So I'll let you kind of take the floor here and kind of let you explain your research. I think it's really fascinating.
Thanks.
So go ahead.
Yeah. So I should mention that when I was on the market for jobs, I feel lucky to be at NYU, mainly because a lot of professors don't get to go back home, right? You're at the mercy of what's available when you're going out on the market, and most of the time you don't get to pick and choose. You just go out, do interviews, and you get an offer and you take it, right? And a lot of people are not where they're working; it's not where they're from, right? And so I felt really privileged to be at NYU because I get to come back home. And my mother, of course, reminds me of this all the time. And she did her continuing education at NYU. So she was at NYU before I was at NYU. So she's like, "Oh, my son's getting to go to my school now, right?"
Yeah.
So my mom was really thrilled that I was going to NYU. So it was a dream come true. And at the time, I was actually interested in doing organometallic chemistry. That's what I wrote my proposals on. Right, trying to do some more CH activation, some base metal catalysis. So we get here, and of course, this is right after the pandemic, so it's a little tough go at first. People weren't around, and trying to get students to join your lab and work the normal hours was really tough. Right, we had shift schedules, and it was just hard to start. But we ended up finding this nitroarene chemistry where we take nitroarenes that are typically inert chemicals, right? You think of nitroarene, the deactivating aromatic ring, right? Solvent really doesn't participate in reactions unless you reduce it to form an aniline, right? But itself, it's just very inert, right? It's really nothing. But we found that we can photoexcite these, and then you form this diradical intermediate, and the diradicals we believe is at the oxygen units, and this can undergo a cycle addition event with an alkene, form a dioxazole intermediate that would fragment, leading to carbonyl products, the formal oxidative cleavage products, the products that you would get with ozonolysis, right? And it just had an inherently good cell because we were doing this dump stir irradiate to get the same products that you would get with ozonolysis. The problem with ozonolysis is that it's a complicated setup, right? You need an ozonizer, it's potentially explosive, you have to deal with all these safety precautions. So I remember when we first got this seed result, we were thinking, at first we didn't believe it. We were like, how are we doing this? We have no oxygen, there's no oxidant in there, it's just coming from the nitro group. That's very odd, right? And so we degassed, we did all these studies to make sure there was no oxygen in there. and it ended up being reproducible, and we realized we have something that might be really special and useful to the community, right? And very practical. We're in the age of sustainability and practicality, right? So people want easy reactions that give you valuable outcomes, right, and valuable products. So we were thinking that this is really good and it would probably be useful. And we were really excited. We were sort of nervous because we were thinking that this is too easy to be true, right? Like most discoveries, like you find something, you're like, well, if I did it, someone else must have done it, right?
Yeah, right.
And you look in the literature, we were lucky that there was really nothing known about it. There was a couple papers out in the JACS 1950 archives that had some mention of this with UV light, but we were using 390 405, right? And this was a bit more practical. So we decided to study the mechanism, and we were able to publish this paper. Getting your first paper is always special, right? No matter where you are in your career, your PhD, your postdoc, your independent career. And we were able to submit this to JACS, and it was pretty well received. And my students were very happy, and it was good to just feel like we found something, right? Because when you start off, it's really hard, right? You come up with these ambitious ideas, and you really have no legs on these projects, and you have to make it happen, but you're also training students, right? And it's just hard. So getting that first result, the first thing that becomes your first paper and sort of gives you an identity and becomes your program is really special. And I remember thinking that, wow, we did it, guys. This is something that I know when you talk to other established professors in the field, this is the moment they're talking about where they realize that being an assistant professor is fun. And I remember thinking, this is the moment, this is fun, and I'm glad this happened to us. A lot of it's hard work, a lot of it's luck, a lot of it's things that you can't control. But, you have to keep pushing, because if you don't push, it probably won't happen, right? So,
I mean, listen, luck favors the prepared. I love that's always one of my favorite saying. What I would love to hear though, how, because like you mentioned, you kind of proposed organometallic reactions. Who was doing this? Like, who was decided to photoexcite nitroarenes? Like, what was kind of like the discovery of this? How did this go? Like, why are you doing that?
Yeah, every discovery has an interesting story, right? Of course, it sounds great when you read papers and you're like, oh, they thought about every single detail
they
of this
hypothesized
reaction.
this.
Right. But some of it may be true, but most of the time it's not really like that, right? You kind of have a serendipitous result. There's some thinking in it, but sometimes it's just something that you just come across, right? So we were doing organometallic reactions. The problem is that things weren't really going well, and we weren't getting these reactions to work. We were trying to do CH activation mediated by like nickel, titanium. We were trying to do base metals because of the sustainability aspect. Things just weren't working. So I was in the lab a little bit and with the postdoc, and we're trying to do this reaction, and we were trying to do something else. Actually, we were trying to get this aryl iodide. We had aryl iodide. And we had alkene, and we had 390 nanometer light without a photocatalyst. And we were just curious, can we just do just photo-induce aryl radical formation, radical coupling, right? That was the idea. It was just very basic, but at the time that we're 2 years in, and we really don't have anything. So we're like, okay, let's just try to get something going that could be interesting, could lead to something.
Yeah.
And then we're starting to think, what if we put other groups on this aromatic ring? Can we get some other types of addition? So we added a nitro group, and then we were getting the cleavage reaction. And I was thinking that, wow, that's more interesting than doing the radical coupling. What's going on here? and then we realized we got something. This is something that's very interesting. We're doing a cleavage without ozone, without oxidant, just a nitro, and it appears that the nitroarene is getting photoexcited, and we're doing this cleavage. And I remember, like, my first project, I doubted it. So I told my student, make sure you degas everything, make sure, like, there's no oxygen there, go in the glove box, do this reaction, and turn out to be reproducible. And then we identified something that's really special. We go back and we realize that there's only one report in 1950 that showed this, and we studied the mechanism. We did a lot of work trying to understand what was going on, because nitroarenes actually absorb in the UV region, not the visible light region. So what's happening? And this became a whole, like, really great, like, research endeavor, and we ended up fleshing out a lot of things, and it became paper. And then this intermediate that we uncovered, this diradical intermediate, we were able to leverage it to do other, like, important reactions such as CH hydroxylation, right, just from this nitroarene. So it was one of those things that was kind of unplanned, but the important thing is identifying the side products. You know, the question I used to hate as a grad student was, what's the mass balance, right? And most of the time you can't figure it out. It's some dimer, some garbage. But I think the crucial moment was we were able to figure out what that mass balance was for that just radical coupling reaction. It turned out that mass balance product was more important than the actual product we were trying to get.
Right.
And that was good. That was really good. And identifying that, and I have to give credit to my student Emma. She was the one that discovered this, and I was able to identify it, isolate it, confirmed it, and we sat in our office just like how you sit in my office with my advisor, planned out, okay, this is something that we can plan out and make into a project, potentially write a grant for, and this could be our new direction. That's when we transitioned from organometallic chemistry to just synthesis, and now we're synthesis.
There you go. That's the beauty of it. Again, full circle, man. Now you're sitting in the office with the students figuring out the project. That's really cool. Yeah. So I guess, now, a lot of your labs kind of centered around these reactions, but I saw in Ken Archives now you can basically capture it and make aziridines, right? So I don't know. So like you also mentioned, you can take aliphatic CH bonds and make alcohols. I don't know if you want to explain a little bit how those kind of work, because I think, do you have to capture the intermediate then functionalize it, or I don't know if you want to.
Sure. So while this discovery was a bit serendipitous, right? After understanding the mechanism, now you get to sort of think about it, right? So once we understood the mechanism, we realized that this intermediate, right, we're forming these two oxygen-centered radicals. One can serve as the H bond activator, the other one can serve as the oxygen atom source, right? So this is where we actually were on the board, just throwing out ideas, trying to figure out what we can do, and that's what's great about understanding things, right? Now you can sort of hypothesize, do a lot of things like this. So now the rest of the projects came based on, like, ideas developing from understanding the mechanism. So this dioxygen radical intermediate that stems from the photoexcited nitroarene, one can serve as the H bond activator, the other one as the oxygen atom source, the heteroatom source. So that was the initial hypothesis, and my student took a hydrocarbon, mixed it with the nitroarene and irradiated it, and then they were able to get the alcohol as well as the ketone, the overoxidation product. So we realized this hypothesis is working, right? And this idea development stemmed from just fundamental reactivity of oxygen-centered radicals, right? And then it worked out. We optimized. We were able to make it selective for the alcohol, and we know that converting a CH bond to a carbon heteroatom bond, such as alcohol, as amines, that's very important, right? If you look at all pharmaceutical drugs, small molecules, or even therapeutic natural products, they all have a heteroatom somewhere, right? And the philosophy of our lab now is, can we take sort of commodity chemicals and do a late stage heteroatom incorporation without oxidant? And the beauty of these nitroarenes, the azoxyarenes, these 1,3 dipoles, is that the heteroatom's internal, and upon photoexcitation, you can transfer it without an oxidant, right? So we can basically extend substrate scope, because the other CH heteroatom incorporation events typically require an oxidant. Right? So that's one of the advantages of using our approach. So the CH hydroxylation came out, and then the next question was, okay, can we add a nitrogen, right? So this became a little challenging. At first, we wanted to use the nitroarene and use the nitrogen that's embedded there, but we had a very hard time of transferring that just an atom to systems, right? We only saw the oxygen being transferred. And so we said, okay, can we develop something that's isoelectronic to nitroarenes and modulate the same reactivity to do a heteroatom transfer event. So if we use azoxyarenes, which is basically taking one of the oxygens from nitroarenes and put a nitrogen there, can we photoexcite that and relay the nitrogen atom? So a very simple thought process based on our fundamental knowledge of understanding our chemistry. And it turned out to work in a way that was also very different, because we thought it was going to do CH emanation. So we thought that we photoexcited the oxygen radical serves as the hat source, right? Just like our CH hydroxylation, and the other heteroatom will be the transfer source. But it turned out that upon photoexcitation, we were actually decomposing that reactive intermediate, and it was spitting out a free singlet nitrene that was undergoing azurination with alkenes. So again, something that we didn't plan, but we had sort of the foundation of a heteroatom transfer. It just happened in a different way. So that's how that story came into play. And we were very excited because now we can transfer a different heteroatom using the same fundamental principles as our nitroarene chemistry, and has the same benefits as well. So we were pretty excited about that.
Yeah, I saw that on Chem Archives. So I look forward to seeing the full story when it comes out, fully published. Just as we kind of wrap up here, I mean, so like now you're still doing a lot of photoexcitation reaction, but probably don't want to give too much away, but where do you kind of see this going, like for your lab? Like, what do you kind of see in the near future?
Yeah, it's a question that I think is very important and hard to answer. Because when I started, I would tell you that I'm going to be an organometallic chemist, right? But now I'm a synthetic photochemist. So 5 years down the road, I don't know what will happen. To be honest with you, it's a very hard question to answer, right? Because I think about like Gevorgyan's career too. He was doing removable direct move CH activation. Now he's doing palladium photoexcitation chemistry, right? So it's a very, in synthesis we're always evolving. So I don't know, and I think that's okay not to know. Right now, I would say that we want to develop economical and sustainable heteroatom transfer methods, or heteroatom incorporation methods. And that's the goal right now. But 5 years down the road, I don't know where we'll be. We'll be probably doing something even better, probably something unrelated. But at the end of the day, what I want to do is create practical and sustainable bond forming events, right? Whether that's with a catalyst or not, as long as anyone can pick it up and do it, and they get the same efficiency, and it doesn't develop a lot of waste. It avoids, like, I don't want to knock transition metals, but some transition metals are very expensive, right? It's hard for users to use.
That's fair.
So, if we can develop things that are practical and useful, I think that would be exciting. Yeah.
Well, Professor Parasram, I want to thank you so much for coming on today. It was a pleasure talking with you and hearing your story, but also like the serendipity of your chemistry. I think it's refreshing for people to hear, honestly. Like, we're excited to see where it goes, honestly. And hopefully the Giants will come back, but we'll see.
Hopefully. All right, Aiden. Thank you so much. I really appreciate this. Thank you.
All right, everyone. We'll see you next one.